thanks for inviting me here. It's good to be back. This talk is based mainly on some work with Ritam Sinha, but also some older work with Klebanov and collaborators. Okay, yeah, this is, I gave a similar talk in ICTS. Okay, so the idea is there's different large n limits, and they're interesting. Okay, so historically the first, the large n limits were just vector models, which are fields with one index, and these give rise to a large n limit where leading order diagrams are explicitly summed. Okay, these dynamics, however, are similar to free theory, so the spectrum of higher spin operators is protected, and they may be dual to higher spin gauge theories. On the other hand, matrix models are fields with two indices, and these give rise to large n limits where the leading order diagrams cannot be explicitly summed. The dynamics is non-trivial, so for instance, anomalous dimensions of higher spin operators can diverge, and in some cases may be dual to Einstein-like theories of gravity. So examples are super Yang-Mills and ABGM, etc. Yeah, so then the motivation for tensor models are there other large n limits besides these, and can we just try to systematically understand all the different types of large n limits, and for a variety, which may be interesting for a variety of reasons, maybe not necessarily just this one. Okay, so tensor models are fields with 3 or more indices, and these can give rise to large n limits in which all the diagrams can be explicitly summed, but the dynamics may be more non-trivial than, say, a vector model. Okay, and these are of course motivated by the SYK model, but they're unitary theories without a random coupling. Okay, so our motivation for studying the tensor models is because if we want to study the diagrammatics, it's a bit easier to study generalizations of tensor models and the diagrammatics in this context, and then maybe later one can try to generate similar models with a random coupling. Okay, so any questions so far? Okay, so so the tensor models we'd consider would be based on fields with, well, we can consider fields with 3 indices or more. So say R indices. Here R is 3, so psi ABC. We'll take
gauge theories with fundamental matter, something like that would also be something that you would like to consider.
You can consider gauge theories with tri-fundamental matter, but the interactions I'll write down would be more complicated than would arise from integrating out gauge fields, say. Okay, so the particular interactions we write down, we just analog as 5/4 or 5/6 interactions, and I don't believe you can realize these so much by interacting in a gauge field, but one could have a tri-fundamental gauge field. But here we can just take it to a symmetry group, say ON cross ON cross ON. Okay, here we take 3 different symmetry groups, ON cross ON cross ON, which allows us to write each of these 3 indices just as a line of a different color, so a Tuft coupling. If I was to take a single gauge group and have this symmetric traceless representation of that gauge group, then the 3 lines would have to be in the same color, which can be studied, but it's a little bit easier when the lines have different colors. And so this is the case we're considering, is 3 or more gauge groups, ON cross ON cross ON, and each line is a different color. Okay.
You also take different values like n and n.
You can take n. Yeah, sorry. Hi. Yeah, so one can take n prime. You can take different n's. For some purposes of my talk, it doesn't matter if they're different, but other purposes there's this like it can be convenient if they're the same because you can impose symmetries, a discrete symmetry. Okay, any questions?
Yeah.
Yeah.
So in Mitten's model, he had four sides, so 4 different kind of sides. So this is clever. This
This is Klebanov-Tarnopolsky style.
So
Yeah.
there is no point in doing the Wheaton's model in any of these things anymore. Is that right? I mean, everything of Wheaton's model is captured by Klebanov's model.
Well, I think so. I mean, I think Klebanov-Tarnopolsky model is a little bit simpler and easier to generalize, and so this is what I'm interacting, but what I'm studying. But of course, I'm taking that and generalizing it. So you could have taken Witten's and generalized it. Maybe those generalizations could be different. I haven't. Okay, but okay, this seems to be this. I mean, Klebanov-Tarnopolsky seems simpler than Witten, so we're starting with that. I mean, I don't have a. Yeah, and it seems better in general. So fields just with 3 indices. We take them different gauge groups. So each line for the propagator can be drawn with a different color. Okay, and we'd consider rank R fields. So there may be more than 3 indices, and there'd be On to the power R symmetry group and R different colors in the propagator.
Sorry, just
Yeah.
You have 3 indices. When you say rank 3, each of them takes 3
No.
values?
I mean, there are 3 indices. R is the number of indices. So
And they take n values. Is that
each
right?
takes n values. Okay. And we'll consider R indices, so maybe 4 or 5 later on, and each takes n different values. So yeah, so in a different symmetry group. Okay, and then so when you have 3 values, you can see what are the different interactions you write down. So you write the 6 fields in your Lagrangian, and then you can contract the various indices in different ways. Okay, so one way of representing an interaction is we use this interaction graph. So here I'll introduce a label for each field here. So these are like field vertices. So 1 is the first guy, second, third, and fourth, and then if 2 guys are contracted by say a B index, that's a blue. That would be say a green line. If they're contracted by an A index, I drew a red line, and a C index is say a blue line. So we represent the index contractions by a graph, where contractions of a given group correspond to a line of a given graph. And or you could draw it in like a triple line notation, where each propagator is like this. And so these are 2 ways of representing this interaction. Okay.
So this is less. This is more irrelevant compared to the tetrahedron coupling.
To center is a sextic coupling. But if we're doing a bosonic theory in 3 minus epsilon dimensions, you might consider a sextic theory. Okay, but look, well, this is just here at this point. I'm just trying to give an example of an interaction. Okay, we'll discuss what theories you could consider in a moment. So you could consider a bosonic theory in 3 minus epsilon, in which case you might have sextic interactions. Or
Shiroman, I missed the
Yeah.
beginning. So you're looking at the most general interaction with this field content. Is this right?
we're going to look at interactions with this field content.
The most general agent, right?
Yeah. I mean, we're starting. We'll study. Yeah, we'll study the most general interactions. I mean, so I'll. So this is one example. So now we want to. So I'll classify these vertices in a.
Having some sort of an symmetric symmetry also.
This does have a color permutation symmetry. So if I interchange, so if you take this graph and you were to interchange the colors, you can relabel the vertices to get back the same graph. So this particular interaction is symmetric under color permutation. So that's an added discrete symmetry. Okay, it also has some automorphisms that don't change the interaction at all. So that has 6, plus there's color permutations as well.
So that could only happen if you have O(n) cross O(n) cross O(n). I mean,
Right.
if the 3 ends are different, then that.
If the ends are different, you don't have that. So we keep the ends same, because then that color symmetry can help you. And
But formally, it should preserve that structure, right? Quantum mechanics should preserve
Well, then the symmetry wouldn't, I mean,
You start with the vertex.
he,
If we start with this and let's say you write down some quantum effect fraction, would that not again at a formal level have this symmetry?
What if there's a trace identity that worked at a small end but not
No, so this is some large end.
when it's larger than
Larger than that.
Yeah.
Then when it will be different.
well, it would relate different models. ON cross ON1, M2, and 3 would be related to each other.
Yeah.
But in this case, it's symmetry of the theory. Yeah. Okay. And so this is still introduction. So this is like these, say, for this thing. So then a correction to the propagator could be drawn this way in triple line notation. This correction I'm calling is called an elementary melon. We can also just, without colors, if you use these numbers, you can specify the width contractions that way. So this is the field 2 connected to the field 2 of this guy, and so on. And okay, so these are the Feynman diagrams we draw, and this is, yeah. So now the question is, what are all the interactions? One.
Are you going with the UN or the ON?
I'm only considering ON at present. Okay, UN puts some more restrictions on what you can write down. I mean, maybe I'll discuss UN briefly, but okay. So we'll consider interactions. So the simplest QFTs you can consider are phi-4 theory, or a psi-4 theory, or a phi-6 theory in 3 minus epsilon dimensions. So we can write down all the interaction terms that one can have in tensorial versions of these theories. So
What is the precise notion of planarity?
I will come to that. But basically, for the interaction, etc., any two-color fat graph should be planar. So if you forget one of the colors, or okay, so it's a little stronger than planarity. But that's what we'll discuss. So for Kugel's 4, as you're maybe familiar with, there's basically 3 different interactions. There's the tetrahedron, which is shown here. There's the pillow interactions, which are not symmetric on their color permutations. And there's this interaction, which is essentially the double trace interaction.
So the last one, if we had 2D QCD with this color structure, then the effective site of the 4 interaction would be of the last one. If you just
If you-
exchanged. I can ask you.
In 2D, if you integrate out a gauge field, say if you did, say, you could get interaction like this.
Like that, the pillar.
But I think for 2D QCD, you would, well, 2D,
Well, any gauge field. If you couple the 2 gauge fields.
so say you have a Chern-Simons gauge field, and you have
Yeah.
UN cubed or ON cubed,
Yeah,
and you integrate out the gauge field, you'll get a pillow,
Thank you.
because you can see that's like double.
Thank you.
Okay, so the pillows are what you get from integrating out gauge fields.
Thank you.
Okay.
I'm sorry,
Yeah.
and maybe you answer this. So if you start with this 4-phi interaction,
Yeah.
you generate these graphs, I guess, but you don't generate any. I mean, why are you writing down these graphs?
These are all the interactions with ON cubed,
Which are quartic.
Oh, I see.
Okay, I mean,
all different ways of contracting.
all different ways of contracting them.
Okay, thank you.
So these are all the interactions you can write down. You could ask which are generated.
Complete set.
Yeah, for quartic interactions. Yeah,
Thank you.
ON cubed, and
And
you could.
3 and 4 dimensions, this is the set of all power counting relevant things.
With R equals 3, rank 3.
Yeah.
Yeah. For the appropriate field theory, these are the only relevant guys. Okay.
Of course, you can just have quadratic interaction.
You can also have quadratic. So I didn't write the quadratic.
You won't perhaps generate them just from the symmetries, 5 to -5 or something.
So for R, so I generally would keep R less than Q, because. So I just looked at the quartic. You can't really have a cubic guy. That's not true.
Cubic could have 9 indices. They have to contract in pairs. How about that?
Right. So this is a graph answer.
Yeah.
So so it is like enumerating graphs you can generate subject to these constraints. Okay, so these are regular graphs because each vertex has the same degree. So you look at all the regular graphs of degree 3, and then you try to color them appropriately, which has some name in graph theory, and that's one way of enumerating all the interactions. Okay, and then
And just to follow
Yeah.
up, Sandeep, so is the quadratic term unique? Is the propagator unique? Just tracing the field.
it seems to be unique because they're all different gauge groups.
Right, it's unique.
Because they're all different gauge groups.
Additional term in the quadratic as a square of that term, but here only had this kind of thing.
Yeah, what about that? What about the quadratic term square? Is that what that is?
This is the quadratic term square. Yeah.
Yeah, there's only one again. for
Yeah.
the same reason.
Yeah.
Right, so you set the coefficient of the quadratic term to 1, let's say.
Yeah.
Then there's a mass, and there's these three. So there are 4 operators here. 4 RGs, 4 parameter set of RG flows.
Yeah. Yeah. Here, if you impose color permutation, then this has to be a symmetric combination. That discrete symmetry. If you don't, then they're different. So now for q equals 6 and r equals 3, there are 8, although I didn't draw the color permutations of all of these. Okay, so this is G1, which, okay, so total of 8. This is a triple trace, these are double trace. Then these are the single trace.
You're going to
Interactions.
compute the beta functions of these guys?
We have a 2-loop beta function at the end, but that's, yeah. But first I'm going to discuss what are the diagrams that contribute in the large n limit for these guys, because it's not obvious. Say that the tetrahedron interaction, like tetrahedron gives you melonic diagrams, do these give you melonic diagrams? Then I'll calculate a beta function perturbative.
So you could have considered even q equal to 4 and r not equal to 3 something.
Yeah, you could try r equals 4 or r equals 5.
Then you might.
You have more diagram, more interactions, or yeah.
And then through arts you might generate others even if you don't start. So you need. To
I don't think you'll change the rank, right? Because that's saying what is your global symmetries on cross on to the power r.
But say earlier you couldn't generate this q term because that was forbidden by the index structure. Let's say you had 4 or 5 interactions. In general, you might generate 3 5 interactions provided symmetries allow it for it. But earlier you couldn't generate it, but now you can generate it.
If you had a different rank,
Yeah, that's what I'm asking.
You're saying the
You
rank is
keep all
even.
the terms.
If the rank is even, at least index count.
in the even you can allow a cubic term. That's true. That's true. So we are not. Yeah. So when you go to larger q, then you also have the lower q operators, and the full RG you write them all down. So that hasn't. We only do RG for r equals 3, but that's possible. That's true. So these.
You cannot quite have it, right?
What are
For
R equals 2 is the matrix model, is a bifundamental theory.
but cubic you cannot write.
You can write a cubic which it's
No,
like
otherwise it works, but not actual
not
cubic,
colors.
You cannot quite color it. Yeah. So I was
Yeah,
just
right,
wondering
right.
whether one has to be careful.
Right. I didn't check you can color these. Yeah. So these are the q equals 6, r equals 3 vertices. Okay. So now we'd like to distinguish between the different types of interactions you can write down. So the distinction we make is, the expectation is the most interesting interactions are those which are maximally single trace. So maximally single trace are those interactions which remain single trace after forgetting edges of all but 2 colors. So this double trace interaction is not single trace, it's double trace. This pillow, although it's single trace, it's not maximally single trace, because if you erase the red line here, it becomes double trace. So, but a tetrahedron is maximally single trace, because even if you forget just keep any 2 colors, you still are left with a single trace interaction. So the expectation is the maximally single trace interactions are the most new, in the sense that the other ones are sort of double trace and hence less interesting. Though you can
Not suppressed in the last one.
they're not necessarily suppressed in the large n. But especially for a larger Q or an R, we might just, to reduce the number of interactions, focus on these. So anyway, so maximally single trace interactions are, in a sense, maybe more interesting. So okay, so for Q equals 6 and R equals 3, the only two maximally single trace interactions are the first two I wrote down. So the first one we call the prism, and if you look, it's like, it looks like a prism. Okay, okay. The second one I call the wheel. Another word is K33 from graph theory, and that's the simplest non-planar graph. So these are the only maximally single trace Q equals 6 interactions. The other ones are double trace or not double trace. And if you solve in the larger limit, these turn out to be not as important, really. Okay, so these are the two maximally single trace interactions for Q equals 6 and R equals 3.
So if you scale your interactions to G1 and G2 such that those maximal single trace of interactions are dominating, then is it that the other ones will be subdominating even if they get
No, they're not subdominating, but it's just like a vector model. The effect on the diagrams of vector models are, you just, like for the ON vector model, it doesn't even affect many correlation functions, just say the scalar. No, these are also there, but the diagrammatics is more trivial.
Is there a sense in which you can Hubbard-Stratanovich-Taylor the other operators? Can you write everything in terms of maximally single trace operators and then their products? If you could, then there's a clear sense in which they're necessary.
I would suspect something like that is true, but I've not worked that out. So
Sorry, what was the comment?
You know, if you take an ON, if you have trace phi squared, then as you guys know very well, you can just Hubbard-Stratanovich it away, right?
right.
So work with this just a single trace theory and some Lagrange multiply fields, and in the end solve for the Lagrange multiply fields.
Right.
So there's a clear sense in which you never need to deal with more than single trace, and then some classical problem. I was wondering whether something else.
But I guess the question, sorry, just to ask,
Yeah.
I guess the question perhaps is, can you use that and only just keep the maximally single trace?
Yes,
right? That was
that's
your
what
question.
It so happens well,
wasn't clear.
yeah. So I haven't. I'm just restricting to maximally single trace for convenience, and it's a natural restriction, but it could be better justified with more study.
So you won't keep the other single traces, the non-maximally.
Well, in the first part, I mean, for these ones, actually, it's not too hard to keep them. Okay, but when we go to higher R, we won't keep them. Okay, for R equals 3, I can keep them, and I do. But okay, we might. Okay, so you might ask what happens with higher rank, like R equals 4 and 5. So we would like to enumerate all the maximally single trace interactions. Now we restrict to maximally single trace because the total number will increase fairly far. So if suppose we want to enumerate all the Q equals 6 maximally single trace interactions.
So I think it probably cannot be done, because if it could be done, then it would just be effectively multi-particling of a simple structure. Oh, but then the question, sorry, maybe I retreat. Maximally single trace operators cannot grow faster than the number of single trace operators for a double line, right?
Right.
So it can grow at most Hagedorn-like. Then you multi-particle that won't grow faster than Hagedorn. But we know that the set of all such operators grows faster than Hagedorn. It grows like n factorial. And therefore, there must be more information than just multi-particling maximally single trace.
You do have to you would have to have lower Q tensorial things or something like this.
Yeah, you have to have more than just.
I mean, it'll be a little bit more of a
Yeah.
non-trivial structure. So okay, let's just see. So you can, if you want to construct all the maximally single trace interactions, you can do that. So for R equals 2, say there's just one maximally single trace interaction, which is a graph where a cyclic graph with alternating colors.
Sorry, I thought the definition was if you drop one color, it should be single trace.
So if you keep all but 2 colors.
All
I mean, no, if you keep exactly 2 colors, you drop all the rest of the colors.
You make it a matrix theory.
any two colors you keep, it stays single trace. So R equals 2, it just has to be single trace. Okay. Okay. So this is the cyclic graph, and there's just one interaction. For higher rank, if you forget any one color, it should reduce to the R equals 2 interaction. So it means you have to construct it by sort of combining cycles together in such a way that if you forget any one color, you get a.
Sorry, that was the definition of maximum.
Yeah.
Forget one color and it should reduce.
Forget all but two colors. So if
Forget all but two colors.
it should reduce to a single trace. So
Imagine the two are colors and the rest are flavors. Don't count the flavors.
yeah. So basically, by
I still try to understand the motivation to talk about
maximally single trace versus.
clear.
Well, from the point of view of graph theory, they can be studied in general, a rank R order Q MST interaction. Some things can be done in general.
But like
But-
Abhishek says, it would be most satisfying if you had some statement of some basis or something like that, right? You can take these and generate everything. That would be the most. Like single trace.
Right. So at present, the motivation isn't, like the justification isn't very
Sure.
as strong,
Fair
but
enough.
it does seem a natural restriction to consider, and it's sort of productive to consider this restriction. So to construct the R equals 3 maximally single trace, you just add 3 blue edges to this graph, such that all the two color graphs are cycles. And okay, we find there's just, if you do it that way, there's two ways to do this, which give you the prism and wheel that we discussed. So if you add this blue-red cycle to this green-red cycle, it gives you this graph, and that's the prism interaction. And the only other way to do it is this. Alternatively, you can add this cycle to this cycle, and that gives you a wheeled interaction, which you can also think of as a Mobius sort of ladder. This is what it's called, and that's a non-planar graph. I mean,
In the
I want to add, so this is a graph with red and green edges.
and that one has got red and blue.
So I want to add blue edges to this.
Okay.
Okay. But it's red graphs would stay the same to make it R
So
equals
the
3.
red links will stay the same.
Yeah.
Then you'll add either
Blue
to the first
or green to the second, and it should, yeah,
But in a way that if you now erase, let's say, the red,
it remains single trace.
Single trace.
Or it was designed that way.
Yeah, so you can now just look at all the ways of adding blue edges and just check whether that property holds. And there's not too many ways to check, so it's just like a few cases. And there's just, so two possible ways of constructing the R equals 3 single trace are either this prism or this wheel. Or they'll be equivalent to this by some permutation. So these are the only R equals 3 maximally single trace Q equals 6 interactions. If you want to add a further color, you would add yet one more color, which we take to be yellow. And it turns out there's just one way of doing this, which is pictured here, and that gives rise to a graph which is an octahedron. Okay, so there's just one R equals 4, Q equals 6 maximally single trace interaction, and you can add one more color to that to get a R equals 5. Okay, Q equals 6, this should be Q equals 6, and that's the most that R can be. So the largest value of R would be 5 for Q equals 6. Okay, so there's,
Can you just show that final diagram?
which one, this one?
Yeah, at some point you're connecting everything to.
Now everything is connected to everything else, but you can color them in a way that,
Distinct.
yeah, one of each color, and all of the cycles you can make. So it stays maximally single trace. Okay, so in some sense, the maximally single trace, you can distinguish the interactions to a few. So again, there's two R equals 3 maximally single trace guys, which are the prism and the wheel. For R equals 4, there's one, which is the octahedron interaction, and for R equals 5, there's this guy, which is unique. I don't have a name for this. Okay.
Shiroman, sorry, I also missed
Yeah.
the introduction, and
Yeah.
if I'm jumping ahead, please excuse me. But that some of these models you'll solve in the
Yeah, so now we'll check that for these, can we solve all the diagrams? I'll show that for all of these diagrams, they're essentially melonic or something like melonic. So at least you can sum all the diagrams for these models. And yeah, so this is what we're going to do. So you can show in general that if you have a maximal rank MST interaction, that is R equals Q minus 1, it's always dominated by exactly melonic diagrams. Okay, it's similar to our order Q SYK interaction.
And non-MST interactions are not generated by MST interactions?
That's not necessarily true. Well, in the large n limit,
And what is the, I'm sorry,
Yeah.
I'm not well enough informed
Yeah.
about all this, but in the SYK case, ultimately the story was that the low energy effective dynamics is dominated by the time reparameterization.
Right.
So there was a sort of symmetry based outcome. Is there something similar here? Kind of a universal story that comes out, or is it very different?
well, the thermalization time was slower for these guys substantially. Okay,
So you
in
don't
that
need the
sense,
chaos
it's not, but of course the spectrum of bilinears and diagrammatics is similar.
But is there a
So-
universal low energy sector corresponding to the analog of time reparameterization or something?
I
that
do
came
not
out there?
know if is
Well, if you have this kind of thing, then there would be in addition to time reparameterizations, there's an ON sigma model, ON cube sigma
That
model.
was your point.
And so the low energy dynamics was not n independent, unlike it was a bit strange.
right. That's
And that was
this.
But I'm not sure that will survive to the field theory. It's very important that these modes are normalizable. And
Right.
The question about whether they're
Yeah,
not, they are or not.
they might not be normalizable in a higher dimensional thing, but
oh, I see.
again, a satisfactory field theory may not exist yet. I'm not saying
Yeah.
that.
So it may or may not. If there's a delicate calculation, the kinetic term for these modes is very infinite.
Oh, so actually, I'm very sorry. You should go on. But
Right.
what is the story for the SYK-like models when you go up in dimension? Is there a universal low energy sector of some sort? Given the analog of the time reparameter?
So if you take a Groston model with a random coupling in 2D,
Probably not then, I guess. It doesn't seem like any. Okay. All right.
right. So, but again, what I mean, we generate these theories. You could probably have similar versions with random couplings, and maybe you have a different. If you choose your distribution for the random couplings, you might get other diagrammatics. Yeah, I mean, here the mode is purely for the graphs. I mean the dynamics, to get more interesting, it would be better to have a random coupling. So the question is, yeah, that's my
Sorry, what is the story of normalizing and what?
You've got in 0 plus 1 dimensions, you get an ON cube sigma.
Yeah.
Now you might, the logic for that was that they looked like they were light modes.
Yes.
But then the question a little bit is that if you take this light mode and you move it a little bit,
Yeah.
is the action for that, is the coefficient of kinetic term finite? In quantum mechanics it certainly is.
Yeah.
But there's some question in higher dimensions.
Right.
And there's this paper by Stanford, Witten and
they talk about that. So
they didn't
aside
talk
from
about the ON part. Yeah, but there was some story of some part of it being non-normalizable, right?
right. That's what something, but
So the ON-Q problem may not be
No, actually they were careful not to deal with the global symmetry part. I can't remember what. So there were some of these modes that would become that would have become very light in quantum mechanics were thrown away. Please correct me. You know this better. You told me.
yeah, this is what they said, but probably some supercharges don't get thrown away. So that's
There was some confusing story. Some of this intuition could go wrong because something that looks very light could develop, has a massless mode.
Yeah.
The coefficient of the mass might be infinite.
How about the time repair? I mean, how about the normal Schwarzian? Does that go over to the
Does
Sharing
the
of
does the
I didn't
you you know yeah
So what is the divergence coming
yeah
from?
Right.
What is the divergence? This extra
You have to derive the kinetic term for this small fluctuations.
So that will have some factors of n, let's say, which was there in
No,
quantum
it's more than
mechanics.
n. It's the fact that you were doing an integral over space.
So if it is compact,
If it is compact,
if it is an IR divergence of that sort, we can make compact.
yeah, no, it's probably not IR. It's probably UV, but the UV modes are in all directions. I suspect it's purely UV. But I know it's so poorly, so I shouldn't make it comment.
Okay, and one
Yeah,
final
yeah,
thing you must
yeah.
know, which is, so, I mean, in quantum mechanics, there was a sort of new fixed point where, you
Right.
know, the kinetic term was irrelevant up to zeroth order, and then, you know, your phi to
Right.
the n dominated, that's why you got the time
Right.
return, et cetera, et cetera.
That's why I also got these other things.
And that's, yeah, exactly, that's right, as you showed. And here, you'll explore, in Klebanov's model, there are interesting fixed points.
yeah we look for the identical fixed point where you drop the kinetic term. I mean the question. And then certain things, like if you want to calculate spectrum of bilinears, the calculation is almost identical to SYK.
And
but-
the kinetic energy term is irrelevant there.
Right.
Then you
But
should
it's a problem. You get so in 1D you would get a Schwarzian, but plus other stuff, which is makes it messy.
Sort of space-time reparameters.
So it sounds like it's easy.
Well, we'll find purely from the spectrum, you always get complex modes. So in that sense, you look for a theory, and a unitary theory fixed point doesn't exist.
But I just want to, just one caution. This intuition I had a lot until I saw, you told me about one
Yeah.
example in the supersymmetric theory in 1 + 1 dimension, in which once again they were able to drop the kinetic term, and yet the theory seemed to make sense. Okay, I thought it would be impossible in higher than 0 + 1 dimensions for this to make sense, because you're just decoupling each point. But somehow that intuition was too fast. It had to do with normalizability of kinetic terms. I had never studied that in detail.
The fixed point by itself makes sense, or you need some all over J kind of.
No, it was a conformal field theory. They actually looked at new conform. This was in 1 + 1 dimensions. This is the reference I remember. It was Stanford, Witten, and others.
Okay, I see.
Okay, and they talked about new fixed points in 1 + 1 dimensions, which they were able to solve by ignoring the kinetic. Sounds totally crazy, but then these modes that Sandeep was worrying about turned out to be non-normalizable. This was
They
like
argued
two
that they're
line
normalizable. I mean,
takeaway.
right. Okay, but okay, so here the question, is a little similar. Just what are the diagrams that contribute in the large n limit? So if you consider an R = 2 maximally single trace interaction, then all planar diagrams will contribute, and you have a
So I just say one
Yeah.
more thing, if you don't mind. What you would expect is now you do the solution, then you do the first 1/j sort of correction to it,
right.
and you would expect to see some huge mess of
Right.
massless modes,
Right.
some uncontrolled.
Right.
But those things that appeared but with infinite coefficient.
Right.
The stiffness was infinite. That was the point. There was no mass, but they had infinite stiffness. The coefficient behind the kinetic term was infinite.
Right.
It's quite lovely. Not that I studied.
Right. So in that sense, it's conceivable that it could happen. Whether it can happen.
Specific to tensor mode. Let's
No,
make
they
it-
didn't even study the tensor. They did the SY.
They did a random coupling. Yeah.
I'm talking about the SY. I don't really know what it is.
Right. Okay. So for a rank 2 MST interaction is dominated by just planar diagrams, which you can't sum. One can show that if you study a maximal rank MST interaction, rank is Q minus 1, then the diagrams are just melonic diagrams, which we know how to solve. For intermediate values of R, clearly melonic diagrams would contribute, but there's also possibility of additional diagrams. Okay, so by studying MST interactions, say with R greater than 2 but less than Q minus 1, there's a possibility of large n limits, which are perhaps more strongly interacting than melonic, but still summable and solvable. Okay, in the sense that they include all the melonic diagrams, but additional diagrams which are non-melonic are.
Instance in which if you take R and Q both to infinity, keeping the ratio fixed, they are something nice.
I've not tried to do that.
So what is rank again, please?
Rank is the number of indices on the fields. So if you have 3 indices or 4 indices.
And Q was what again?
Q is the order of the interaction.
In the usual model, in which you had, let's say, you could have certain large Q interactions, or your index in the field also increased with Q. So that was the kind of thing, like ratio is 1 in that situation.
You could, but of course it depends on the interaction. You also have to specify the interaction. I mean, it's not all interactions of a given rank and Q are the same.
The number of terms of that sort grow as Q goes to infinity, right?
They grow as Q goes to infinity.
But if R is set to Q minus 1, then it's unique.
Is it unique?
It's not unique. Whereas I mean, for Q equals 8 or 10, I think it's unique, but eventually it becomes not unique. Yeah.
Oh.
Well, there's also a question of does it exist? But in some cases, it's not unique. So it's not.
And goes to infinity. Number of terms goes to infinity as Q goes to infinity.
I don't know if that's proven, but you might expect that.
Even with this maximal rank, this R equals Q minus 1?
I mean, no. For arbitrary Q, like if Q is prime, you can construct some graphs using, there's. But there's a question of existence of graphs with certain properties. So which it's just a technical question, but it might conceivably, certainly numerically, then there's cases where it's no longer unique when Q is larger. So it might get bigger. So it could be that it increase. Yeah. Okay, but say you're studying a quantum mechanical model, so you just have this one interaction, and you can see what are the diagrams which contribute. So if R is Q minus 1, if you assume that you have an R equals Q minus 1 MST interaction, then you can argue it's dominated by melonic diagrams. Okay, and roughly I'll sort of show that argument. And when R equals 2, it's all planar diagrams that contribute. And intermediate R, melonic diagrams will be leading order, one can argue, but additional diagrams might also be leading order. So there's a hope of maybe large n limits which have more than the melonic diagrams, but are still solvable. Okay, and so since R is the number of colors in the lines and it's less than maximal, we use the word subchromatic to define these models. Okay. Yeah. So for Q equals 6, there are 3 subchromatic MST interactions. So there's the prism, the wheel, and the octahedron. And what we'll do next is we'll determine which diagrams survive in the large n limit for all these theories.
Subchromatic because Witten and someone did the chromatic or whatever.
Well, the maximal interaction
Those guys did it.
is done, but also because the maximal one is very similar to just a general Q SYK. So it just gives you melonic diagrams. Whereas subchromatic well, there's the possibility of non-melonic. So we'll find in the prism there are some non-melonic diagrams. The other ones, it turns out to be melonic for both of these. For Q equals 6, yeah. Yeah, so I can review the graph theory of the tetrahedron and how that leads to melonic diagrams first, and then we'll do the same analysis for the other guys because people aren't familiar. So let's just review the tetrahedron, how you determine what diagrams contribute when this is your interaction. So it can be drawn in 3 different ways, and we can forget one color to give a 2-color fat graph. That's familiar from matrix models. Okay, so I'll argue that for a diagram to be maximal, all the 3 fat graphs you obtain have to be planar. Okay, so this is a diagram where if you forget any 2 colors, the graphs are planar. Whereas this diagram, if you forget one color but keep 2 colors, there's one of these fat graphs will be non-planar. So this is not a leading order diagram. Okay, so in this sense, this is why more indices make it easier, because you have more constraints.
That seems to get more factors from the red guy, right? And less factors from the green guy.
Which, this one or this, the first?
The one below.
Yeah, so this is not leading order because one of the graphs here is not planar.
But the other has more dominance, right?
Yeah. So the top one is leading order.
No, I mean the color-wise. The bottom row, color-wise, if one of the color gets you less factor of n, the other color may get you more factor of n, right? Or not?
Well, we'll prove this statement in a moment, but the intuition is that all the fat graphs have to be planar.
If you omit all but 2, you cannot get more than planar.
Disconnected.
Oh, disconnected.
Well, if it's maximally single trace, one can argue it's not disconnected. Because okay, that's one of the advantages of maximally single trace.
That's why maybe.
Yeah. Right. Well, yeah. So then it's a little different when you have double trace, like interaction. You can do those. So like for vector model, it's not really planar that you're thinking of. You have disconnected bubbles that you add. So that's the thing. So okay, and then then once you have that result, then you can show that all the diagrams which are planar for any fat graph are recursively generated by replacing propagators by this elementary melon. And that's what we mean by melonic. So this is the outline of the argument.
So everything can be generated by just insertions of this.
By replacing a propagator by this. That's what we mean by melonic.
Got it.
Okay.
So then the standard technique.
Well, yeah. So now I'll just flesh this argument out in detail with the graphs. So this is what we're going to show. Okay. So consider a connected Feynman diagram with no external edges. That's for the free energy. And we can label the two-color fat graphs as RG, RB, and BG. Okay, and let F total be the total number of loops in the graph, color loops which determines the power of n. And let F, RB, RG, and FPG be the number of loops in each two-color fat graph. So if you add these all up, you'll get the number of red loops times 2 plus the number of blue loops times 2 plus the number of green loops times 2, which is 2 times the total number of loops. So we have this first relation, which tells you the power of n. Now for each individual fat graph, the number of faces plus vertices minus edges is the Euler characteristic, which is 2 minus 2g. And that is less than or equal, that's less than or equal to 2, because g is 0 or higher. Okay, and since your interaction involves 4 fields, twice the edges is 4 times number of vertices. So you can plug that in here, and we have FRG is less than or equal to 2 plus V. You have the same relation for the other fat graphs. So if you add them up, we get twice F total is less than or equal to 6 plus 3V, or F total is less than or equal to 3 plus 3 halves V.
Sorry, what was FRG again? The number of loops in the RG?
Yeah, that's the number of loops in the red-green fat graph.
Got it. Thank you.
Okay, so here there's 1, 2, 3, 4 loops. Yeah. Okay, and then if you add for all the different fat graphs, you get twice the total number of loops, and that's less than 6 plus 3V. Or the total number of loops is less than or equal to 3 plus 3 halves V. Okay, so that tells you basically the largest power of n. So the free energy would be proportional to n cubed, and the Tuft coupling should be g times n to the 3 halves to get a well-defined Tuft coupling. Okay, so this is the Tuft coupling for the tetrahedron, but it's not enough to tell you what are the diagrams that so this is the natural Tuft limit, and we see that the maximal diagrams are those which are planar with respect to any two things. Now next we want to, well, now we want to show that it's those diagrams which are maximal can be enumerated by the recursive procedure I told you.
So in the previous thing, you showed that the maximum number of n that you get is that.
Yeah.
But maybe that is equal to the one that is given by the melonic diagrams. But can one see quickly that no other?
No, so I'm going to show that in the next 5, 6 slides. So you can check that melonic diagrams will give you this power pretty easily. Now the question is, are those the only diagrams of this power? And that I'll do. That's the next stage of the argument. Okay, so yeah, but this is just telling you what the Tooth coupling should be.
So far, you've not used that there was a tetrahedral interaction.
All we use really that it's maximally single trace, which it so happens tetrahedron is the only one. But we'll do the same thing for a general MST interaction with Q and R in a moment. We used it here, but all this can be generalized pretty easily to rank R and Q, which we will do shortly. Yeah, I mean. Okay, when I wrote this thing, if there were disconnected components, you would have multiple Euler characteristics. Okay, but because it has to be connected, that's, yeah. Okay, so this is the Tooth coupling. Now the question is, how do we argue that we can recursively, only the melonic diagrams are those ones which contribute?
Sorry, there you are not using maximal, just MST, right? You are using just MST.
Where?
It's maximal MST when you say that it's not disconnected.
No, I have to do this for each 2-color fat graph.
Yeah.
So that means maximally single trace.
Yeah.
Because
But not, sorry, I meant this R, this kind of thing, not R equals Q minus 1 kind of.
yeah, we're not using that. So this works even for subchromatic guys. Okay. So it can be any R as long as it's maximally single trace. You can have a similar. I'll show you the similar Tooth coupling, and basically all the 2-color fat graphs have to be planar. So to show now that we can recursively enumerate it, first step is to show that each free energy Feynman diagram contains a loop which passes through exactly 2 vertices.
Sorry,
Yeah.
if you don't impose this maximal MST here, the MST here, then the n would be allowed to be more or less. It could increase, right? It could be more than that.
I don't understand the
If you draw diagrams
yeah.
with something that is non-MST, then would they be suppressed necessarily compared to?
No, the question is then what would be the Tooth coupling for this? You can always find a Tooth coupling where they're not suppressed.
No, but let's say you use the same Tooth.
You can modify this argument to tell you what the Tooth coupling should be for a thing which is not maximally single trace.
But Abhijit is asking, suppose you use this scaling and then you take one of these non-maximally single trace guys, could they be super dominant compared to what you've given?
Well,
Could they tell you that those are actually the dominant?
for those ones, no. If those are super dominant, then that means that then your limit would diverge as you got more. Well, I don't remember what the Tooth coupling is for those. I think those are weaker. If you use this Tooth coupling, those would be suppressed. But you use a different one, whichever one, just keeps the leading order diagrams. I mean, I can check what the Tooth coupling is, but yeah. Okay. So to show that the diagrams, only melonic diagrams contribute, we show that each free energy diagram contains a loop which passes through exactly 2 vertices, and that's called a 2-cycle.
So this is the case which is subchromatic, whatever.
Well, in principle, I'm just doing just the tetrahedron again. This is a review of the tetrahedron. The subchromatic presented in a way that it's easy to generalize to subchromatic. So
melonic totally dominate here, is it?
yeah, and then we'll use the same. So I'm showing the argument which shows that only melonic dominate. it, then we'll apply the same argument to the other interactions. Okay, so the second step in the argument is any free energy diagram which contributes, which is maximal, contains a loop which passes through exactly 2 vertices, which we have to prove, and that's called a 2-cycle. Okay, so the way we do this, let's denote the number of loops passing through n vertices or n cycles as squiggly f sub n. So f2 plus f3 plus f4 equals the total number of loops, because any loop passes through some number of vertices. And if you get twice the number of loops passing through 2 vertices plus 3 times the number of loops passing through 3 vertices, etc., equals 6 times the total number of vertices, because if you look at a given vertex, you get 1 blue loop, 1 red loop. I mean, there's total 6 lines passing through it. Okay, so we have these 2 relations for the number of loops passing through n vertices. Then we also know that for the maximal graphs, f total is 3 plus 3 halves v, so we can replace that here and now add these 2 together and eliminate v to find that basically 2f2 plus f3 equals 12 plus f5 plus 2f6. Since these are all greater than 0, we have twice the number of loops passing through 2 vertices plus 3 times the number of loops, but plus f3 is greater than or equal to 12. Okay.
So just to be totally clear, say you start with 2 different interactions.
Yeah.
With interactions in G1 and G2. Now you can scale both G1 and G2 with their respective tooth couplings.
Right.
Then the dominance, which one dominates is a very complicated question. Neither one of them will dominate.
Yeah, you can include both of them.
That would be more.
That's what one would do. Yeah.
And so far the statements that if you scale only one of them, then that one.
No, I'm just telling you how do you scale any one.
Any one of them, but once you do more than one, then that is a complicated question. And can you sum them or not?
You use very similar techniques. It's just slightly more tedious because there's more diagrams to draw. But the same recipe will tell you what are the diagrams that contribute. Okay, you can find what are the diagrams that contribute and check if you can sum them or not.
Because there could be mixed tests now.
Yeah, you can have mixed ones. So this argument I'm presenting for just tetrahedron for simplicity, but you can do it for other interactions as well. Okay, and it can be modified similarly. Okay, and in general, it may be tedious to determine if it's melonic or not. So actually, okay, but the upshot is here we have the graph theory tells you have a loop passing through 2 vertices or a loop passing through 3 vertices. But you can argue that any loop you try to draw that passes through 3 vertices, just by enumerating the possibilities, has to have a non-planar fat graph. So there are no maximal loops passing through 3 vertices. So you just have a loop passing through 2 vertices.
And these arguments are totally independent of space-time dimension. So I can.
Yeah. So this is purely diagrammatic.
As well, I can try to do it in quantum mechanics. And then
So this is primarily quantum mechanics. To say, I have no claim that these models would exist in higher dimensions. Yeah.
okay, so in quantum mechanics, if you have for a given large enough cube, you have 2 different kind of couplings, and then you can look at the height between them and see what kind of field theory you are getting at IR.
Right.
Are you getting something more than just equidistant relations?
You can do these sort of things. These sort of games can be.
Sorry, you say I wasn't paying attention.
So if you had 2 couplings, let's say you scale them such that both of them are dominating, if only one of them is scaled. But now because 2 of them are scaled, so they will fight between each other, there will be mixed graphs. Now even in quantum mechanics there is a question of what happens in IR then. What kind of theory you get?
Right. So you can ask that with this wheel and the prism that I told you, and we haven't done that yet.
Because time reparameterization will still be a symmetry, but the fixed point, nature of the fixed point will change because the equation it has to satisfy is different.
Right. So here, this is for tensor model. Then you can also try 2 different random couplings, and then where you really have a.
You don't really expect to get anything but maybe changing the number number play. Because just symmetry dictated that.
Symmetry says that, but this is more than symmetry. In that particular model, you can show the others do not appear. This is lowest order one and exact. But here, lowest order you will still get that number.
Yeah.
But the nature of the fixed point will be different. What I mean by that is that, say, what is the value of 2-point function at the fixed point?
A value of 2-point function is the high dimension
Of high dimension of
Yeah,
particle.
but all that is
That's not universal
yeah.
stuff.
Only J, just one scale characterizes the entire Schwarzschild dynamics. Doesn't matter how it arises, what the approximate CFP is that couples, all totally irrelevant. Just one number, that's it.
Here you will have only one scalar. No.
Yeah, I mean, the best you can hope for is you get less higher operators if you wanted less of those to make it more realistic. That's what you can hope to get.
Also,
Yeah.
I don't think any of this will eliminate the ON modes, or even those will continue.
No, they are totally separate. They are there. They are there.
Right.
There may be more interesting stuff in higher dimensions. This business about the normalizability or not may depend on something.
Right. So now we've shown.
Just
Yeah.
you must go, but that was a very strange comment what you said, because the gravity analog of saying that in IRD you don't expect these time reparameterization modes is that it costs an infinite amount of energy to make the boundary fluctuate in ADS3 or higher, right? ADS2, the boundary is one-dimensional, so it can fluctuate at finite cost energy. But the fact that there are examples, you say, where they can
They cannot.
that's exactly what happens.
It's
Oh, so then,
substantiating.
right, okay. So then that's exactly what's happening.
Right. But the strange thing is that the kinetic term is not there.
Is irrelevant.
This
So
is like
that,
what-
that's the argument.
Right. So now any free energy diagram has this 2-cycle, which is a graph basically with two. There's this loop which passes through exactly 2 vertices. So now you can draw a 2-color fat graph for that diagram, and it would look like this. So once you draw this 2-color fat graph, you see that planarity forces whatever is inside here has to be disconnected from whatever is outside there. Otherwise, it wouldn't be planar. Okay, so planarity splits. The forces that these 2 subgraphs in and out cannot be connected to each other except by what's shown. So they're effectively disconnected. Okay, and that tells you that all the free energy diagrams have to look like this, like an inside subgraph and outside subgraph, which are disconnected. And this is effectively saying melonic dominance. I mean, to be more precise, you can argue that this diagram is leading if and only if each of these are maximal, because the only index structure this in can have is straight lines, and you can check this index structure. So this index structure is equivalent to just in with a line coming out here and out coming here. And now each of these individual diagrams, this out at this in are maximal, are free energy diagrams, so they also have to be maximal, and then you have a recursive characterization. Okay, so that's the proof. And once you have this, these are the sort of diagrams you would draw. So it's effectively, this 2-cycle effectively tells you what the elementary melon looks like. Okay, so this is the argument for melonic dominance in this model. Okay. And
Shiroman, when as you know very well, when you have planar, when you have just in the planar limit for, let's say, vector models,
Yeah.
You have some nice path integral Schwinger-Dyson kind of derivation of gap equations,
right.
using things like trace factorization. Do you know if there is something like that for this?
I don't think so. I mean, there are some papers by these European guys where they do complicated stuff with auxiliary fields that I haven't gone through.
But nothing nice and simple, you say.
Well,
Have you tried to find such an argument?
My first few attempts didn't work, but I wouldn't say that there isn't an argument. Just that it's not. I've not seen it present. I don't think it's known.
Okay, thank you.
Okay.
You didn't try to derive the generalizing equations independent of factorization.
We independent of diagrams. Just write down.
Just equation of motion and path and gate, then learn dynamical.
Right. So at the first graph, for the tetrahedron, it's not. I've not seen it, and I've not been able to do it. Okay. What might be able to do is you might be able to use Schwinger-Dyson equations for other things to reduce it to a tetrahedron. Okay, and then. So as of now, I claim there's there's none, but we haven't. Yeah, I've not convinced myself it doesn't exist.
But you've tried. I mean, you made a serious attempt to try this.
I didn't make a very serious attempt. I mean, it seemed like it doesn't work, and just do some of the diagrams. Like, see, I've not made a serious attempt yet. What may be possible is for the higher order, more complicated interactions, you can use some Schwinger-Dyson to reduce it to a tetrahedron. Okay, but the tetrahedron, I don't know if the Schwinger-Dyson can work. Yeah, so here's just the straightforward generalization. So first, consider any maximally single trace interaction. There's R, choose two color fat graphs. Yeah, and this is why, of course, we have to do all this graph theory but maybe this graph theory can be translated into something more abstract.
But I was wondering whether that would teach you the structure. Like the graph theory sounds like a lot of detail, but maybe there's some principle. Whatever.
Yeah. But okay, the graph theory gets a little bit more complicated for these other guys, slightly more. So maybe, so there are choose two different fat graphs, and if you sum over all the loops in each fat graph, it gives you R minus 1 times the total number of loops, because, okay, by just similar arguments. So this determines the power of n. Okay, and we now argue that it's fat. So for any two-color fat graph f alpha, f plus v minus e is 2 minus 2g. And since qv is 2e, that tells you f, the number of faces satisfies this relation between q and v.
So it's basically identical.
It's just basically identical with q and v different. So we find lambda is, the free energy is proportional to n to the power r, because there's r colors, as you expect, just the elementary graph we n to the r, and lambda is r times q minus 2 over 4.
So this part was as easy. The part that's going to be
This
more
part
difficult is showing the equivalence of the melonic dominance.
Yeah, is going to be, has to be done sort of on a case-by-case basis. So this is thing, and works for any maximally single trace guy, whatever q and r are. So this is what the Tuft coupling should be. I guess for q equals 6, it's, it's a simpler form. And next we show that there exists a two-cycle loop passing through two vertices. Because I'm going to focus purely on just combinatorics, I also include one cycles, which would be a loop passing through one vertex, and that's really a tadpole. So you could drop them, but suppose you have a momentum-dependent vertex or something, you wouldn't. So I just include that possibility as well. So again, this part is identical to what I said earlier almost. So these are the total number of loops, is the sum of loops passing through n vertices for each n, and that's related to the number of vertices. So putting it together, if q is 6 or greater, we have this relation, that the number of loops passing through one vertex plus 4 times the number of loops passing through two vertices is greater than or equal to 2qr. So each Feynman diagram contains at least one cycle or one two cycle or both. Okay, but this isn't also enough for this applies also to any MST interaction with q equals 6 or greater, but it's not enough to show melonic dominance. Okay, so we next have to consider the implications for each of the three interactions. So the recipe is as follows. So we know that any free energy diagram is of one of the following three forms. Either it's just the free energy diagram, or it contains a one cycle, which is this, or it will contain a two cycle, okay, with this graph G. So now we'll, of course, saying that it contains there may be several inequivalent two cycles. So a two cycle would be, you have to choose two vertices to contract, and because the graphs are complicated, they're not all equivalent. So you can list all the inequivalent one cycles and two cycles that are not related to each other by automorphism or color permutation symmetry, and that classifies all the free energy diagrams. Okay. So for each inequivalent one cycle and two cycle, we now look at the constraint that the two color fat graphs are planar. Okay, so a two cycle would be, like, you might say that this field 1 is connected to 1 and 2 is connected to 2, or something else. So you specify two Wick contractions for the two vertices, and some of these Wick contractions are equivalent by color permutation symmetry, some are inequivalent. So we first just list all the inequivalent two cycles you can have, and then do analysis for each inequivalent two cycle. So how planarity works is that okay, so we have these labels for each of these outgoing lines. So when you choose the two colors you keep, that forces these numbers to be arranged in a given cyclic order. So for the red-green fat graph, it's just 1, 2, 3, 4, 5, 6. But for the red-blue fat graph, it's 1 to 6, and then 3, and then 3 goes to 2, and then 5 and 4. And for the blue-green, it's 1, 2, and then 2 is connected to 5, and 5 is connected to 6. So you have, the vertices have to be arranged in a given cyclic order depending on what fat graph you keep. So now that then tells you that when you draw you have to draw the two guys you're connected in a given order. And that can, for instance, it can split this graph into two pieces. Or it could be that for a given contraction, you are forced to have a twist, which means that contraction is non-planar. So basically, by these two things, you can rule out some diagrams and hopefully get to a place where you recursively enumerate them. Okay, are there any questions? Okay, so if basically the main thing is this thing that, because when you put it in cyclic order, this graph splits into two pieces. So if for all the two color fat graphs, you can split this bigger subgraph into just 4 individual subgraphs, you effectively have a proof of melonic dominance. Okay, or if you get something more subtle, and the way, if you've argued that this graph splits into 4 different ones, then you can use a cutting and sewing argument to just argue that, this graph is maximal if and only if these two graphs are maximal. So you effectively get a recursive enumeration. Okay, and another way of saying it is all the diagrams can be generated by this melonic. So, okay, so this part is clear. Okay. Yeah, so now we'll do this for the wheel interaction. Okay, and I will not draw all the two cycles. Let's just do two examples. So this is a two cycle connecting line 1, 1 to line 3, 3. Okay, sorry. Yeah.
Sorry, I have to run,
but I think this is yes, fine. Thanks.
Sorry about this.
Okay. Yeah. So 1, 1, and 3, 3. So this, splits up the graph into these three pieces, and okay, here are 4. So if you look at the individual fat graphs, you see that they have to be separately connected, and this particular two cycle is now effectively of this form, and that's melonic. There's another two cycle 1, 1, 2, 2, which is a little bit more complicated. So if you trace these out and see the ways it can be connected by planarity, you get two possibilities. You get either this this melonic guy, or you get this thing which I call a double snail, which has basically two one cycles, and it's a tadpole, so you would prop it in some cases, but combinatorics allows it. Okay, so ultimately for the wheel, what one shows is that it's melonic dominance, where each line is replaced either by this elementary melon or by this elementary snail.
That could be like a self-energy. Yeah.
Correct. Yeah. So there's two terms.
Theory could come.
Yeah. So this basically you replace propagators either by this or by this for the wheel. Okay. And then you can repeat that any number of times. Okay.
It's these done with the exact. These graphs with the exact propagators.
With the exact propagator, and the exact propagator has these two guys. Yeah.
These were the ones corresponding to the wheel or the
This is for the wheel. So this guy is new in the sense this is slight generalization of melonic, but
still under control?
well, all of them will turn out to be under control. So it's a slight generalization, but you can argue it's not. Okay. Next is that octahedron. I'm going to do octahedron first, then prism, because prism is a little different. So prism.
Sorry, this is the question that I asked earlier. So if you take those now,
Yeah.
the ones that dominate, and compute from them, let's say some vertex, the sextic vertex from these things, would this now have the same topological structure as this like the wheel?
I didn't understand the question.
I mean, if you consider corrections to the vertex using these diagrams, would it
Right.
again be of the same type, wheel type, or now everything will be generated?
Well, all the diagrams so you can sum all these diagrams up, okay, using only a wheel here and a wheel here. Okay, so in that sense, you don't have to check about those other guys, but we do RG, and you do generate. I mean, I do believe you will generate the other guys.
But then somehow with that vertex also, then somehow this perturbation is under control.
Well, the point is, any vertex generated by this perturbation theory should be under control in the large n limit. Okay, I mean,
So you can expand this bare set of vertices also, right?
well, I do believe maybe we do RG with all these interactions at finite n just in epsilon expansion, but that's not all orders in n. Okay. I think one can do an all orders in n RG for these, but we didn't do that yet.
Leading order.
Yeah, or not orders. I mean, leading order in n, but all orders in say epsilon. We do a perturbative RG later, like a two-loop RG at finite n. Okay, but and that's a good question. For the octahedron, the analysis turns out to be simpler because there's actually more colors. So there's 6 fat graphs, so there's more constraints. And you get just completely melonic theory.
All these graphs are doing is changing, effectively resumming the propagator.
Effectively resumming the propagator.
I mean, at least.
Yeah, they're all resumming the propagator.
So it's a question of basically weak contraction. You can ask your question at the level of weak contraction. I don't know the answer, but the graphs here are not very relevant.
Of course, okay, this is for free energy diagrams. So then you look at the free energy diagrams and you cut out some legs open.
Okay.
So it's a little bit more.
So then for Abhijit's question, would you need to take more diagrams into account?
Well, you don't necessarily to take more diagrams into account, because it's like if you were to sew up the lines, you'll get a free energy diagram. But a given free energy diagram, you can think of it like when you cut out the lines open, you can think of it as being another vertex.
I see. So the set of graphs, even for Abhijit's question, would be under control.
Yeah, set of graphs will be under control. I mean, it's just that
Okay, but then I said
you could have generated because you generate a graph like this and you choose some lines now to be external lines by cutting them open.
So my only point is that if at large also you're generating other terms, then you might as well include that here to say that even with this additional thing, it's under control.
Right. That's what you're right about that. Okay, so again, with the octahedron, it's also traditionally melonic, and a similar analysis works. Okay, so that octahedron interaction is melonic. Finally,
so other terms would be non-maximally single trace.
well, there's two questions. You can ask. So here I did the wheel interaction. And there's just the wheel interaction. You can ask if I include a prism, which is also maximally single trace, and we do include that.
Yeah.
And the diagrams are under control. I mean,
Right. And then you could ask about the non-maximally single trace. Now you might guess from analogy with
We're trying to get to some closed set.
yeah, so so the idea is here I'm you'll essentially argue that each diagram contains a cycle passing through two vertices. Now those two vertices you take to be maybe one wheel, one prism, two prisms. So any two of those from the set, then you enumerate all the different two cycles you draw, and you see that you can split them up into this type of a thing.
But you might guess from analogy with, let's say, vector models or matrix models, that the ones that are not maximally single trace will come with extra factors of 1 by n. Just because they have extra powers of n in the numerator. Right, I mean, so suppose you've got let's say we're doing a vector model. You have double trace, so that term is n squared. So it will only be generated, if you didn't start with that, with a factor of 1 by n. You might guess that's how it is. But I'm not sure.
For QGLs 6 and 4, we want to control these non-maximally single trace guys do not generate maximally single trace.
Right, but the other way around, do the maximally
They do
will.
generate, yeah.
But you might guess that those will be generated with factors of 1 by n, even though they could contribute at leading order. Like, suppose you take a double trace guy
Right.
with a vector model.
Right.
That's order n squared. Therefore, its coefficient will be generated with a 1 by n. And that thing is the right order to contribute. And the same order as an ordinary, order 1 for a single trace. I suspect that's how it works.
No, yeah, for these cases, it works just like matrix and vector.
Yeah.
Okay, in the other cases, higher Q, it's
Maybe.
not proven that it works in general.
But you may want to count that as leading order anyway, because it will contribute.
So here is a wheel, and the octahedron is also melonic. Okay, the prism vertex is slightly not melonic. So for this cycle, it breaks up. The subgraph breaks up into individual guys, but for this particular two cycle where you take 1 and 1 and 2, you get the following three flat graphs.
Would have been precise if you had the earlier statement correct, that you can generate all others by single trace kind of things. So the same question,
Right. So you might be able to argue these things in general. So this is the two cycle for. These are three fat graphs in the prism interaction, and the constraints are a little bit weaker from this guy. So this tells you 1 and 3. 3 and 3 have to be connected separately, but 4, 5, and 6 on this side can be connected to 4, 5, and 6 on this side. So we get a weaker constraint, namely that this free energy diagram doesn't split into 4 individual guys. it splits into one individual guy and this blob connecting 6. Okay, and okay, but you can so if you trace the colors through this blob connecting 6, you'll see that this is maximal. This diagram is maximal if and only if this diagram is maximal. So this has 2 vertices, this has 1 vertex. So now this diagram has to be one of the 2 cycles considered earlier. So you still have a recursive enumeration of graphs. Okay, and if you draw this thing sort of backwards, I mean, this move to this move is effectively like taking a vertex and expanding it like this. So now we have a recursive enumeration, but instead of also replacing propagators by self-energy, you replace a vertex by a double vertex, this sort of vertex expansion move. And this graph theory tells you that those are all the maximal diagrams. So it's, and for instance, this is a diagram which if you check, it's maximal, but it's not melonic because, well, you know, it's not melonic, and if it's sort of like this vertex was expanded. So you take a melonic diagram and you expand it. Okay, and this is like there's 12 total loops, so it's n to the 12 g cubed, which is lambda cubed n cubed. Okay, so this is a non-melonic diagram with the prism interaction, but it is of course still summable by this rule. Okay. Now of course, but okay, I did this analysis for the prism, but the prism it's sort of not as interesting because for the prism, well, first this is the summary. So we showed that all the 3 subchromatic interactions give rise to solvable large N limits. The wheel and octahedron give you traditionally melonic limits, and the prism you have diagrams which are not traditionally melonic. Now it turns out that for the prism you can rewrite it via an auxiliary field as a tetrahedron interaction.
This is the same as the gate boson exchange. The prism was the one that was this guy?
No, that was pillow. So prism, it was like, should I go back to the, I'll draw it here. So it's, I mean,
oh yes, this is sextic.
it's like a prism like this.
Yeah.
So
Thank you.
yeah. Well, yeah, and then you draw this.
Yeah. It's not the gate boson case, because the gate boson itself carries indices.
Yeah, so the way, but you can still, what you can do is you can sort of split this up like this.
Yeah.
Okay, and now this is like psi ABC, psi ABC. Okay, and now this interaction is like phi AB is like 3 of these. Well, if you just glue this into a single field, it now turns to a tetrahedron. So if you could collapse all these into a new field with 3 lines, then that's a tetrahedron. So it can be reduced to a tetrahedron, and but 2 fields, and then you sum the diagrams. Okay. So it's not maybe genuinely new large N limit, but that's from the point of view of sextic theories, it's a different set of diagrams that contribute.
So melonic dominance of the prism you could have shown just from the tetrahedron and then expanding that to one of the vertices.
Yeah. So I'll well, let me skip this. This is the spectrum of the 4-point. Let me go straight to this guy. So this was the prism interaction, and you group these 3 together. And now I write this tetrahedron where one of the fields is an auxiliary field. But with indices, and I have this guy here. So if you integrate out chi with this tetrahedron, you get a prism. so
One of the auxiliary field has indices, it makes up part of the prism,
yeah,
and then it has a very simple.
yeah. So like this sort of this face of the prism is grouped into a single guy. Okay, and then you can use the usual approach, but you have these two fields. Okay, this dashed field is the auxiliary field, and this auxiliary field is also, if you think of it, if you were to plug this back in here, it's like vertex expansion. Move. So yeah, but no, there are different gap equations. So you can solve these, and we did solve them. So this is the gap equation. And I can discuss the solution, or I can rush through it, because it's you have to be a little careful. When can you neglect the kinetic terms, and that's puts some restriction on the scaling dimension of the fields in the IR limit. Okay, and this is the restriction basically from that. Okay, then to solve the for this
that restriction is just that the dimension of phi to the 6 is lower than the dimension of two derivatives and phi squared.
well, also for the auxiliary field. So you have two different restrictions.
Oh, I see.
Okay, and the dimension of you can draw. So the auxiliary field has this sort of disconnect term. So you have to drop this guy
Yes.
and this guy both. So there are two constrictions.
And that gives you the two ends.
That gives you the two ends.
I see.
So that also unitary bound left.
Yeah, I think one is the unitarity bound. And
So Shiroman, when you have reached the auxiliary field description, where the auxiliary field itself is not a singlet,
yeah,
then can you do further manipulation to make it
a singlet.
look like, in terms of singlet?
Yeah, so this is what I've not been able. I don't.
Because
No,
at
that-
this stage it's not clear that the
Yeah, so-
is large and limit.
Yeah, but only from the graph theory earlier, it's because it's a tetrahedron. We know that it's a large limit because the first part of the diagrammatic analysis using graph theory tells you there's a large limit. But rewriting it in terms of singlet, I do not know if I don't think that's been done. I mean, but yeah, the idea is for more complicated interactions, you can certainly try to reduce auxiliary fields, reduce it to lower Q, or to this maybe a tetrahedron or a few base cases. But these base cases, I'm not sure how to solve using singlet fields.
Is there a way of compactifying to quantum mechanics to generate these interactions? With, let's say, some gauge-mediated interaction, some tri-fundamental interaction in the higher dimension, and compactifying it generate them?
Well, you mean other than integrating out gauge fields, you're saying? What do you mean
I
compactifying?
mean that you have, let's say, R cross S2, compactify on S2, look at energies much lower than scale of S2. See what is the quantum mechanics.
Do the different modes interact in a? I've not considered.
So it's bound, sorry, Shiroman.
Yeah.
I would have thought one of the things would be that if you take del phi,
Yeah.
and compare with phi to the 6, that the phi to the 6 is more relevant. That would have been one of the conditions, but I'm not saying.
And that should be here, this guy.
But if I do that, phi to the 6 has 6 delta phi, and del phi has 2 delta phi plus 2. So I'm not doing that comparison. But I don't get D in my comparison.
Okay.
Scaling dimension is d minus 2 minus delta.
Scaling dimension is D minus. Thank you. That's probably that.
Are you
Yeah. No, I was misunderstanding. As Naveen pointed out, I was thinking delta phi was your dimension of your operator. It's the anomalous dimension.
no, delta phi is the dimension in position space.
But it's D minus 2 minus delta phi.
No, in momentum space is A.
Okay, good. So now let's go back. So then going back to what I was saying. So let's do the dimension position phi to the 6th
Yeah, so
has dimension.
well, phi cubed times del plus delta phi. So 3 times delta phi plus delta chi, and that should be bigger than
Yeah.
this.
But so
Delta, how would you fix in delta chi?
Delta chi, okay. Well, we can even look here. So we know f naught and g naught dimensions from the free guy. Okay, so g naught would have,
F naught is the chi and the g naught is the phi.
yeah, f naught is the f naught is the chi, g naught is the phi. Okay, and so f naught is dimensionless, and g naught is 1 over p squared. So this is p squared. So now I want a. I just look at what a and b have to satisfy in this thing to make these two guys dominant, and I drop these two.
But suppose I was really naive.
Yeah.
I just went back to the Lagrangian.
Right.
The Lagrangian has a del phi, and it has a phi to the 6th.
Right.
I don't do all your complicated.
Right,
yeah,
right,
yeah,
right,
sophisticated.
right.
Okay. I would have thought very naively the question of kinetic term dominance.
So 6 delta phi
6 delta phi is I know it's very naive.
is less than,
Is less than 2 plus 2 delta phi. And that you're telling me is wrong. It was a very naive argument because I'm assuming that there's no, that the dimension.
no,
of
well,
phi
well,
to
well,
6
no, well, sorry. So there's a coupling in front,
doesn't matter.
and that coupling I'm taking to be, I mean, will be dimensionless in t equals 3. It won't be like in your bare Lagrangian. Like you have a coupling in front, whose dimension depends on the.
So the coupling doesn't matter. It's just a question of whether the operator itself is more important in the IR than the other operator.
No, but if you think in terms of this about certain which, then the interaction of phi with chi and the chi square both could be relevant than the kinetic term, right?
Yeah.
In that sense, the interaction is causing something.
Yeah. I think what you're in my language. I think what you're telling me is I'm being too naive in saying that the dimension of phi to the 6th.
No, we're going
dimension of phi.
This must be the case.
Yeah. It's interesting because it worked for SYK. If you thought this way for SYK, it just worked.
It worked for SO.
This is almost the same as SYK. I mean, I think this is just a.
But so is my algebra wrong?
Maybe you should, in one case, phi to the 6th would be a renormalized phi. Your d phi is not renormalized because you have this lambda. I mean, I know that lambda times phi to the 6th has dimension d.
But I'm not talking about engineering dimension. I'm talking about the dimension of the operator in sense of RG. It should be that the dimension of the operator phi to the 6th in terms of RG is smaller than the dimension of del phi, right? Because that's when it will dominate.
So your answer would work for d equals 6, d equals 3.
Okay. That's where it's dimensionless, you say. I feel that there must be a way of saying what Abhijit and you were saying, as saying that my assumption that the dimension of phi to the 6th is 6 times dimension of phi is wrong.
Yeah, well, that would be wrong, but it's a complicated contraction of them. So we do, yeah. So, yeah, that operator has a different dimension.
From 6 times phi.
6 times 5.
Why shouldn't it? Yeah.
I mean, if I take chi to have dimension d by 2, because, and then compute the dimension of phi, then would it work correctly?
Yeah, actually, because there was phi cube chi.
Yeah.
Chi had dimension d by 2.
D by 2, and then that would work, right?
So then 3 delta phi should be this. Interaction is 3 delta phi plus d by 2. Sorry, yeah.
Yeah, it works.
Can be written in terms of
It
two
works.
part functions.
Because then phi cube must
There
contribute
is
d
no
by
delta
2.
phi.
So d by
power
6.
counting. If it
Oh,
can
no,
be
it's the
written
same.
in
It's the
terms of
same
two
thing.
part functions, this is part functions, that's right.
Well, here chi doesn't have the same dimension as chi.
Yeah, I think the fact that
If you include these couplings, you can do something naive.
exactly. What I was saying was right, it would have to be that chi had the dimension of 3 times phi, which you won't find. Right? Yes, you're somehow telling me that this composite operator is different from Yeah, which is fair.
But this confuses me because this kind of thing you can do in general dimension, any dimension. So,
If you can derive these equations from an effective action, which involves only let's say 2-point function of phi. So chi is integrated out, and then if it is written only in terms of self-energy and 2-point function,
Yeah, where will
if you
the
know the
other?
dimension of
Yeah.
2-point function, then you know if it is relevant or irrelevant. And the check is that if that dimension matches with the dimension of chi, the one that you said, that chi has that 3 times the dimension of phi or not.
Yeah, but he's done the calculation. He knows the answer. Just my words are not fitting somehow.
Right, right. I mean, but whether you do it position or momentum space, you have the, you just, can you drop the Kinetic term as these constraint on A and B. Yeah, and
You know A and B, you can just quickly check this fact that if delta chi is 3 times delta phi or not.
it is, well, we will
If what I was saying was right, the delta phi would have to be d by 6, which presumably you're saying is not the case, right?
right. It's not. It's not. It's less than d by 6. In the normal melonic thing, it's d by 6.
Yeah, that's what I mean. That's where my intuition is.
Right. So here now to solve for delta phi,
what do you mean normal melonic?
say I did with a different, not a prism, but say I did a sextic, a wheel or octahedron, or the R equals 5 case, which I didn't discuss, where it's melonic and not, there's no vertex expansion rule. You get that sort of, you get d equals 6 simply. Here actually you can't solve the dimension for a phi by dimensional analysis.
Yeah.
You have to itself do these integral equations to get the dimension of phi.
Yeah, so this is somehow genuinely new.
And that's it. It's more complicated because just getting dimension of phi.
You can't look at it and say.
You can't look. Yeah. So earlier you could look at the equation and figure out. Here you can't look at it.
Lagrangian and see, right?
Yeah, yeah. Even and then yeah, Lagrangian and see it. So here you can't do that. So you get this sort of. So if you just do dimensional analysis here, you get the same equation from both, and the two unknowns.
That's the point.
That's the point. And
So you have two variables, and you've got two equations. You do dimensional analysis, you get the two equations.
well, these two equations are the same, and you have the two unknowns, which are delta phi and delta chi.
So even the power is not obvious until you solve it.
Yeah, so you have to do this integral, and you get equation like this, and then you plot it. So this range is the allowed range, and say in 2.9 you can find a dimension you like.
You are not guaranteed to have an intersection in that range.
Yeah, I mean numerically.
That you have a solution.
Well, once you have this equation, we can check there's intersection in the range. But I mean, you would look. It might have been there's not even intersection in the range.
And sorry, and what was 2.9 again?
So this is the equation to solve to find delta phi
Yes. And
from these things.
and
So now I solve this, say, in d equals 2.9.
in d equals 2.9. And could you solve it in d equals 2, for instance?
You can solve it in d equals 2, okay, and you get a reasonable scaling dimension. Okay.
So even and you believe the solution exists in integer.
The solution for delta phi exists. We'll see the bilinears will have a complex dimension.
What happens with 3? D equals 3, sorry.
Well, d equals 3. This is then it's free, and so you have to go to a little less than d for this IR limit to solve. Yeah. So for d equals 3, I guess this is the same.
We don't quite know what is relevant or not.
Yeah.
So in that sense, I should just set d equals whatever I want and see whether the intersection exists in the
Yeah.
A priori,
I don't know.
Expect
Yeah.
it, right?
Yeah.
But I was saying
So
just
it stops existing after 3, right after 3?
Well, after 3, this range goes to 0.
Oh, I see. Okay, I see.
I mean, another way to say it, if you want to think of this as a flow from a free theory, then it could only be
With a sextic operator.
with the same.
Yeah.
Well, okay.
So that
So here you literally can't go d greater than 3. Like in the other cases, you could formally do it.
It works.
Yeah, so this is the thing, and this is the equation, and it gives you a delta phi is 0.456, and delta chi is more than 3 delta phi, because that's 1.53. Okay, so now you can also look for bilinears.
Doesn't that more or less say that there is no factorization and there is no normal kind of realization thing here? Because if it was to be the case that there is some usual kind of thing in terms of bilinears and so on, then there's some kind. I mean,
Well, not for these variables, sir. I mean, I guess, yeah, that's why. I mean, you don't look for one because it doesn't look like I haven't. I mean, I can't say that there's not some really complicated thing. Like I'm not. A traditional, just if you try to follow the standard approach, it doesn't seem to work. I mean, unless someone can. Yeah. So I mean, it looks like there isn't one, and okay. So then you can look for bilinears, and there's 3 different bilinears. There's phi bilinears, phi chi, and chi bilinears, and okay, the bilinears of types A and C mix, but so that gives you slightly more equations. But we can still solve as before. You get a kernel and you look for eigenvectors of the kernel, and for d greater than 2.8, we get a real spectrum of bilinears, which is real and finite. But for d less than 1.68, but in this window, you do get a complex scaling dimension for the lowest bilinear. So that tells you there's not a unitary theory in d equals 2. Okay, so although but okay.
For this d greater than 2.8 and d less than 1.6, would you say it's unitary theory? Usually
Well,
something goes wrong, right? For fractional dimension. It's not.
no, so I guess for the fractional dimensions, we didn't see a problem. I mean, maybe there's some other operators that have complex dimensions, but it seems it appears in the epsilon expansion you can do a theory in d minus in 3 minus epsilon dimensions, but it won't extend all the way to 2.
No, but Abhijit's saying if you try to make sense of the theory in d equals 2.9 dimensions, if you do it carefully, you see that there's trouble. I mean, this is the stuff.
Well, what trouble do you get in a 2.9 dimensional theory?
You find these evanescent operators that have, well,
So they're usually made up of a bunch of phi's and chi's. Not just two.
No, there's evanescent operators in fermionic theories,
Okay.
right? Because the gamma matrices and
Well, I don't quite know what it's called there, but I thought the one that just caused problems for unitarity. Because roughly there's some d minus 1, d minus 2, this kind of thing appears, so how would you get something?
so something with many some sort of a differential form type.
Yeah.
even I don't know exactly what it is, but I thought that Richkoff and company studied precisely this question, trying to see, could you try to make sense of these quantum field theories as unitary theories in arbitrary dimensions, and they ran into trouble.
Even in epsilon expansion.
Including a scalar phi fourth.
Complicated enough.
You're saying just
Yeah,
a
the common
phi
factor
fourth
is
in 4 minus epsilon.
Yeah. 5 to 4 instead of 4 minus epsilon.
Okay, so that problem would continue to be here. I mean,
So
but
in order to see that, you would have to consider more complicated than ABC, right?
presumably you'll have to do more complicated ABC. So here we are, I mean, you're using the epsilon to get, you have this Dyson equations that's work in D. I guess you're only in D equals 2. Okay, but so the epsilon expansion, these guys are real. I mean, in 2 minus epsilon, 3 minus epsilon, but there's not a unitary in D equals 2.
But if you were to be non-integer dimension and somehow get unitary for all the things, it would be interesting, I think, in some sense.
Well, I don't think it would be, I mean, if you have a non-unitary theory in phi 4 or phi 6 theory, you'd get that should still be present here. But yeah, and this is sort of how the calculation goes. So these guys mix, and you have these pictures. You get a kernel, and you which is a matrix, and you find the G equals 1. So I'm rushing through it because you might have seen it before, you might not have, but it's again you just want those eigenvectors of this integration kernel with eigenvalue 1 correspond to allowed scaling dimensions. So we solve G equals 1 here, and that's this guy. Okay, now you can look at renormalization. So this action is a special case of this most general action. So you just have 6 scalars with K1, K, these are indices, and you just let me just have a coupling G, K1, K2, K3, K4.
Sorry, could I ask, for any values of the couplings, is the potential positive, not unbounded from below?
Yeah, so this is the prism is manifestly positive,
Okay.
definite.
Okay. And even though that's the case, you get trouble.
Even so, that's the case. But I told you, even in the matrix models, if you do an epsilon expansion, you can get complex
Right.
dimensions.
Right. Right. So the fact, let's say that we were genuinely interested in this prism model in D equals 2. Okay, so now this is something you could do. You could start with the free field theory and perturb it with this operator, which is a relevant operator, and go see where it goes.
Right.
So it has to go somewhere. What do you have a guess for where it would go? Yeah, but you had a putative guess for the fixed point, but it turns out not to be right.
Right. So I guess there's two things. One is you can. Here we didn't include the wheel.
So what is the putative guess?
Well, the putative guess is putting lambda equals. I mean, that we can drop these connectors. So it's sort of like lambda equals
Why is
infinity.
that not the right thing?
Because it gives you complex dimensions.
But you're saying that can never happen.
Well, if you've got a well-defined theory, it should give you.
Yeah. So either you get like a mass, an infinite mass, or something in the field.
It becomes you're saying it could become a gap theory, or there's some other conform.
Yeah. Or there could be, okay, here we neglected the wheel altogether without just justification.
The wheel.
That other interaction. There can be some interplay with the wheel, or there can be a mass, or there could be a phi-4 coupling that's added actually, which gets.
Maybe that's the thing. Why not? Why not a 5-4 and you just get.
So that actually could be studied more carefully. I mean,
Yeah.
If you do the following, you scale the prism diagram, the way it should be scaled according to this count.
right.
But then it will generate other diagrams at subdominant orders, presumably,
Right.
consistently. So at those orders, add the other diagrams too. So now this is a closed set, and now try to study if there are solutions,
You can write down the most general
because they will fight.
interaction with all the things in the large n limit, including all sextic and quartic terms, and only finite. I mean, the diagrams that contribute would be innumerable. So you get some Schwinger-Dyson equations, and then some of the couplings would be either 0 or infinity, I guess, or with some ratios. But and you can study that and see what you get. Is that what you're?
So in case of vector models, if you have a double trace interaction that comes with a subdominant power of n, provided that you have scaled your operator such that your single trace operators are, let's say, giving action order n. So I'm saying that scale your prism diagram as you want to get the dominant,
Right.
but then keep all the diagrams it generates, but with certain dimensions, with certain scalings of n, the one that it will generate, if it generates.
Right.
And then study the whole theory using these kind of techniques and see if you can get a consistent solution. Not complex, but consistent. Because they are contributing in the leading order, right? Because of the scalings.
Right. Right. I mean, that can be done, and also there's the quartic guys. Yeah. These can be done, but I guess it can be difficult in practice to do all these.
So there are no known consistent IR conformal field theories of the form of dropping the kinetic term in 2 dimensions with any interaction.
Right. Now, this if you do the supersymmetric guy, the spectrum apparently is real. So, but it's more the problem you're saying of the some modes. I mean, there's some modes you can argue from supersymmetry the kinetic term doesn't go to infinity as you'd expect. So those are bad for that reason. But that has apparently, at least at the level of bilinears, it has a real spectrum, from what I understand.
But just in your context of just
One field,
yeah,
there's none. Yeah,
there's no known.
yeah, there's none.
Yeah.
Okay, and
Meaning that this is an attempt to, you can view this as an attempt to try to construct new fixed points of the rectangle.
This is how exactly. This is how I am thinking. But then why? So his approach. He has only one kind of diagrams. I am repeating. So if you keep all the diagrams, it will generate all the relevant diagrams up to marginal. It will generate with suitable powers of n. And then you try to solve that system. Then probably this
With
is
arbitrary constants.
with arbitrary constants which are scaled properly with n. Now you solve this system. This should have a solution because this is
Maybe, or
if
maybe
it has.
it's possible, but it's possible that there's no conformal field theory with where you drop the kinetic term.
That is the possibility of course. I mean, this is the bad possibility.
Yeah.
But this is one thing that might also happen that you might
If there is
Yeah.
any unitary fixed point, right?
What? Any unitary fixed point. I mean, with this field content, yes.
Yeah, with this deform. So I take this, deform it by the prism, let's say, and analyze the flow. See where it leads.
What about Wilson-Fisher fixed point with this field content? That kind of in 2 dimensions.
well, okay. What we can do is, I mean, we can do an epsilon expansion. Is what at finite.
The RG flow equation.
Okay, so let's what we can do is say we take all these 8 couplings. Okay, and that's basically so there's a you can calculate the beta function for all these 8, but in 3 minus epsilon dimensions, and it'll be just order epsilon squared, which is like a 3 loop or something.
all of the one epsilon squared. Sorry.
The first non-trivial, not all orders in n, just a 2 loop. Not 2 loop because it's sextic, so that's like 3 loop or something like that. But the first non-trivial correction to the beta function.
I'm sorry to keep interrupting, but can I ask a remedial question?
Yeah.
Suppose I took phi ABC, the whole thing squared.
Yeah.
Just phi to the 4.
Right.
That's trivial to solve in large n.
Right.
And that will presumably give you a good solution in 2 dimensions.
Right.
So this is a putative fixed point.
Right.
Now it could be that this thing actually goes to that. Is that a possibility?
Phi AB is the vector fixed point, is what you're saying? Or?
Yeah, exactly. The fact that it was n cube is irrelevant. You
Right.
make it becomes a theory with n cubed or n cube symmetry.
Right. So that's a candidate fixed point.
That's a candidate fixed point. We know it exists. Now this fixed point has how many relevant operators?
Well, once you start with just a vector model, the other guys don't get generated.
Right. So if we just think of this as an IR fixed point, it's just got the master. It's got one
Right.
relevant operator. So to reach this, you could do like a 1 parameter tuning to reach this. So if you've got even 1 parameter there in your UV theory, you could reach this. So okay, so let me make a conjecture. Conjecture is that the actual physics of this is this theory.
The vector model fixed point. And that also works because for the matrix, if you consider the matrix, just the theory with a matrix and a vector in 4 minus epsilon for phi 4, there's also a complex fixed point in the epsilon expansion.
I see.
If you just consider the matrix theory. And so So that theory could also presumably flow to the vector model fixed
Yeah.
point. Whereas,
Sorry, when you say complex fixed points, etc., this is by making an error, right? Of if ignoring the other.
Yeah,
terms. So
I'm saying, okay, by complex fixed point, I mean, if you solve for this beta function, so in an epsilon expansion, you could have a complex, you have this beta function, you look for a solution, and the only solutions, and you have a solution where one of these couplings is complex.
but I thought just the fact that there's some positive definiteness of the energy and so on would imply.
Well, in some, it's saying a real fixed point doesn't exist. So if you consider a matrix, I don't know if I have it here, okay, but at some point, if you consider a theory where it's just phi ij, okay, phi. So this is your single trace matrix guy, plus you have G double trace. Okay, so these are okay, and you study this in 4 minus epsilon dimensions. Okay, with the proper scalings of these guys. You of course you have a fixed point where lambda single trace is 0 and lambda double trace is non-zero. But if you want lambda single trace to be non-zero, then it comes up. Then you can have this be non-zero and real, but then lambda double trace comes out to be imaginary.
But
So in some sense, there's no real fixed point with lambda single traces.
So there's only one fixed point
In some sense, but if you were to somehow keep if you had a Schwinger-Dyson approach which kept,
no, but is it because it's not a positive definite?
no, this is positive definite because it's just a matrix.
Positive definite. Why is it positive? The second term I can see to be positive.
This is like, I mean, it would be like, I mean, I'm pretty sure it's positive definite. It's like, yeah. It's trace of m to the power 4.
That's the double. Yeah, that I agree. No, first trace of
Well, here, if you draw it in this way, like say I draw it like this. So this is each field, and these are the contractions.
Oh, you mean
So it's sort of like this thing, whole thing squared. I mean, this is still.
if you have trace A dagger, that's real. Trace of A dagger. Now m squared is n squared.
So you can never reach it starting from physical real. No, in other words, if you plot when you could even take this and see what goes to what fixed point, right? If you start with the real values of GST, GDT, then presumably you never reach that point, or will you?
You never reach this. Well, this is imaginary, so you can't reach this. This.
This says that in this example, that if you turn on all the scalings, then there might be a situation where you have made one of them large by scaling. That is wrong. But you might find an optimal scaling for which you have a solution.
Right. So there should be some solution. It could be where double trace chi goes to infinity and the rest are 0.
Yeah.
Or the simplest would be or just the mass goes to infinity as a gap, or the double trace chi goes to infinity.
Sorry, I propose we let him finish.
Well, you're more or less finished. I mean, so this is the so you can sort of ask these using RG at finite epsilon, and this is the RG equations for all these 8 guys, just the first non-trivial order. And here these scalings were chosen just from the equations themselves, not from the graph theory, and it has a non-trivial fixed point, which corresponds to what you get from the Schwinger-Dyson equation, at least in order epsilon, and they match what you get from the Schwinger-Dyson equations to the order epsilon. So I mean, it seems like at least in an epsilon expansion, this fixed point, a fixed prismatic fixed point exists, which
And this matches with the fact that you saw trouble at some
at finite 2.8. Yeah.
Yeah.
Yeah. You know, there could be, you know, there's a unique fixed point here, but if you go to one higher order, there'll probably be additional fixed points generated in the epsilon expansion. And that could correspond to a wheel or prism and wheel. And okay, so there's just one. So from the graph, we found the most general rank 3 sextic tensor model can be solved, and you can study it in different levels of care. We've not looked at even a prism and a wheel, which would have a new fixed point. Second of all, if you go to higher Q, these subchromatic theories might give rise to diagrammatic rules that are even more general, which could be relevant for quantum mechanics models. Like the prism is still closely related to melonic, but perhaps at higher Q there's more general things. So that's the end of the talk.
Maybe I can just
Yeah.
ask the question and you can answer
Yeah.
all that. Sure.
Yeah.
Okay. But the question I want to ask is this: that just broadly, what you're finding is something very interesting, right? You're finding, forgetting about all details, you're finding at the diagrammatic level, the theories with more than two graphs and more than two indices are, as far as you've been able to see, are always solvable.
No, I mean, I think for higher Q, you can generate examples which will not be solvable.
Which will not be solvable.
Well, some of them would be like the Q is, if R is even, you can literally just make it a matrix model with just doubling the lines. Okay, but for R equals 3, they're all solvable. Yeah.
Yeah, so I was going to ask whether there were genuinely new, difficult large elements.
There'll always be a
that are not
subset of
matrix
planar.
space.
If you're considering maximally single trace, there'll be a subset of the planar diagrams. So they won't be more difficult than the matrix
Yeah.
theory, but it could be, they would be more difficult than melonic.
More difficult than melonic?
Not, they're never going to be more difficult, I believe, than matrix limit.
And do you have some
Is what you're asking.
Okay, maybe we can go for lunch.
Yeah.